Go out and help someone is the best we can do. There's someone who needs someone to help, you might too. We have our own ways of thinking. We argue about our views.
Well, welcome everybody to our lunchtime environmental talks. This is sponsored by the Ministry for Social Justice and the Environment from the Brazos UU, or the Unitarian Universalist Church of the Brazos Valley. And we feel that the environment's very important in our social justice encounters. I listed the talks that we've had so far. We've had a number of it's in the chat box. We've had a really good number of talks. And I'm stepping down from this role, and I just got promoted to professor, and they tell me I'm going to president of the UUCBV, and I'm told I'm going to get a pay raise of about 3 times what I'm doing. I'm looking forward to that. And so we've had, a lot of talks on the environment, about how to conserve water, what happens to things that we recycle. We had the Pollution 101 that many people liked. Global Weirding by Alan was it was weird. Yeah, very weird. So today we have Professor Alfredo Garcia. He's from Texas A&M University, and he is in the Industrial and Systems Engineering, and he will give us a talk on Texas electric grid. Everybody's wondering what happened. So how can we prevent that in the future? And I just want to let everybody know, if you want to see the video of this talk or any of our other talks, all you have to do is go to brazos-uu.org. And John Faber is trying to get most of the recordings up there. And we didn't actually record the very first ones, but we do have some slides from those talks. Right, there's a link. But if you just go to brazos-uu.org, you'll see something that says lunchtime talks anyway, or you can just search for it. All right, so Professor Garcia. Oh, we have to thank Professor Garcia's wife, because she's the one who volunteered him through Nextdoor, Pebble Creek.
That's right, yes.
Okay, you can go on ahead.
All right, thank you for the opportunity. Let me say a few things about my relationship to this type of problems. I'm from Colombia, South America, and I major in electrical engineering. I did a lot of power engineering as an undergrad, and then worked for the government down there when they were in the process of restructuring or deregulating the market. And in Colombia, the situation is a little bit different, but the market is also exposed to these rare events related to El Nino. Maybe you're familiar with the El Nino phenomena, the increasing temperatures in the Pacific Ocean create these patterns that affect pretty much all these countries that have coasts in the Pacific, Colombia, Ecuador, and a little bit Peru, but not as much. And so we have a drought when El Nino occurs, and then the year after we have the opposite effect. It's a very wet year, and this happens every 5 years. And the problem in Colombia was that the country power system was 70% hydro. And so hydro, when there's water, has zero marginal cost, or very close to zero. And when there is no water, it has infinite marginal cost, but there's no water. So you can imagine how difficult it was for a country that has mostly hydropower to deregulate and make sure that the market forces were going to internalize this risk. So I did a lot of work as part of the government down there to try to see how could we address these things. And lo and behold, many years after I left Colombia, came to the US, and now I'm at Texas. I see it's pretty much the same situation that we were facing in Colombia. It's not the same phenomena, but it's the same problem, the same technico-economic problem. And that's what I want to share with you today. Okay, so what I'm gonna do today, this is the outline for the talk. I'm gonna describe the market design features. So how is it that electricity markets work? And why is it that sometimes certain market designs are not good for dealing with these rare events? They don't have the right mechanisms in place or the right incentives for making sure that we are decently covered against this type of rare events. And I'm going to survey some solutions that have been tried elsewhere, because this is a problem that has been recognized pretty much everywhere there's been an electricity market. Something like what we went through in Texas has happened. And so some other markets, even here within in the US, in the Pennsylvania, New Jersey, Maryland market, PJM, they also have mechanisms in place to try to address this phenomenon. In particular, they are called capacity markets. And so I put the word capacity in red because it's not quite the same notion of capacity, the nameplate capacity that we're accustomed to. The concept that we're accustomed to is, if you look at the nameplate of a plant, it says nominal output. But capacity here is a different type of concept. Is how much is this plant able to produce under a very severe weather situation, right? So it's a big qualification, right? And the qualification is under this very rare event, what amount of capacity can we expect reliably from a particular plant? And that's the kind of capacity that we are going to be talking about. And then the other potential solution to, or remediation for some of the problems in Texas, in ERCOT, is the ability to couple with adjacent markets, because you will see in a picture that some of the markets that are near Texas were not as badly affected, and they could have conceivably exported power to Texas during those times. And this is not, unfortunately, an option right now. But it could be changed. It could be changed as easily as simply investing in interconnection lines. But this opens up certain technical issues that I'm going to try to briefly describe. Okay, so electricity markets. So this notion of electricity markets is relatively new. It started out in the UK with the Thatcher government, and also in Chile at about the same time. And then there was a wave of many countries that started deregulating their electricity markets. And Texas, the state of Texas, as you all know, started ERCOT, the ERCOT operation in 2002. And before that, electricity was considered to be a natural monopoly, right? So a natural monopoly is typically subject to government regulation, and all these activities that go from generation, bulk power generation, and then transmission over high voltage lines, and then distribution over lower voltage lines, and then retail, which is the measurement and keeping track of who owes who. Retail were considered to be typically in a single utility would do them all, and you would get a bill that was essentially the result of a rate-making process by which the utility would go to the regulator, show their books, and then the regulator would say, yes, I think these investments were reasonable, and so I'm going to allow you to charge consumers this much. This is typically the picture of the supply chain, right? So we have on the left-hand side a power station. This is where there are lots of economies of scale, or there used to be lots of economies of scale. And the natural monopolies are always kind of tied to the notion of economies of scale. So with big economies of scale, it's very difficult to have anything resembling competition. And in the old days, if you were to build a power plant like a nuclear or coal, there are significant economies of scale, and that's why it was considered to be a monopoly, natural monopoly. Well, if you go further down the supply, the transmission networks, nobody would ever consider have competition in this type of activity, right? There's only one set of lines that are going to be used for transporting power from one end to the other. And same for distribution lines. Distribution is also a network, an infrastructure, And it would be completely crazy to have competitions having the separate set of wires attending the same type of household. So these two businesses in the middle continue to have this strong economies of scale, but in the 1980s, with the advent of some breakthroughs in the technology of gas-fired engines, jet engines, actually, it was aviation that did it. The generation of power with gas, natural gas as the fuel, started to have it started to be more scalable. So in sense, you could build very efficient plants, not necessarily at the huge scales that you needed to build to achieve efficiencies for coal or nuclear. And so with the advent of this new technology of gas-fired, relatively small-scale power plants, many people believed, and in particular, this is the reason why the UK deregulated, that we could introduce an element of competition in bulk power generation. And so to do that, the ingredients of the deregulation recipe were the following. You would disintegrate the businesses. You would no longer have the same utility doing generation, transmission, distribution, and retail, but you have different businesses. And so in addition to this vertical disintegration, you would introduce an element of competition in generation. So meaning that a utility was not forced to buy from its own power or affiliated or subsidiary power plants, but it could go outside and look for a better deal from some other independent power producers. And so to make sure that the market was going to be receiving or identifying the right cost, the optimal cost of power, a spot market for generation was introduced. In a spot market for generation, this is what ERCOT does. So ERCOT receives the bids from all the generators in the state of Texas every day on a daily basis, and then they find which is the most efficient way of dispatching the demand that comes from utilities in the state of Texas. And then transmission and distribution remain regulated because they are monopolies. There's no room for competition. There is a little bit of competition, though, in the way of expansion. Who gets to decide, who gets to actually build a new transmission line could be subject to some auction or a similar mechanism for competition. But it's not the same amount of level of competition that generators are exposed to. And finally, and this is critical because some of these utilities were formerly vertically integrated, like, for instance, I don't know, TXU. For instance, TXU, I think, is now called Vistra. They did everything. They did generation, large scale. They did transmission, large scale. They did retail, large scale. So in order to ensure that third parties could compete, right? So independent power generators could sell to the subsidiary of TXU that is now in charge of retail in their service areas, then you had to have these ideas of open access, right? I can sell access all those wires that you own because they are open to everybody who has a better deal in terms of generation cost. So the problem with electricity is that as a commodity, is philosophically, if you will, this notion of electricity as a commodity was at the foundation of all these reforms, right? Well, let's treat electricity as a commodity, and we see that commodities are, there are fairly competitive markets for commodities. Why not electricity? Well, it turns out electricity is kind of special. First off, is still not storable. Even though we have more and more capacity to store electricity, there are significant technological advancements in this area. It's still, for the most part, non-storable, right? And so production has to meet demand in real time. This is a significant challenge, right? You cannot, this is not like when you're trading stocks, right? These are pieces of paper, well, no longer pieces of paper, but these are artificial construct, right? The stock share, owning a share in a company, these are financial obligations. Here we're talking about a physical obligation, and so we need to have a third party, which is typically referred to as an independent system operator, who would make sure that this market would operate in the way it is expected, right? So it would keep the balance between demand and supply. So there you have already one feature that is unlike many other markets. You know, nobody is in charge of clearing, let's say, the market for soybeans, because you know, there's a storage for soybeans. There's no need for people to consume soybeans on the spot. And so, whereas electricity, it's a basic necessity of life, people need to consume it. So somebody has to make sure that there is this real-time balance between supply and demand. And that's why we have entities like ERCOT, which are basically market makers. They receive bids from parties, buyers and sellers. They make sure that everything is operated in the way it must be. They have control over the operation of this network through which this market is going to take place. Now, demand of electricity is also still highly inelastic. It may be less so in the near future when people have their own solar panels in their roof coupled with a battery. So you could have intelligent households that could essentially buy from the electricity market when they think it's a good deal, otherwise self-supply. And that would introduce an element of elasticity in the market. But as of today, this is still not quite a fully mature technology, and in many places, this is non-existent. To further complicate matters, there are so many technologies that are used to provide electricity, right? So ranging from nuclear, coal, fossil fuel, gas, and then renewables, right? So as we know in the state of Texas. So just a few things about the structure of costs of all these technologies. So this is a very useful picture that tells us how competitive are these technologies. And on top, we have the alternative technologies of renewables, right? So you could see onshore wind has the lowest of all the renewables in terms of levelized cost, dollars per megawatt hour. The blue bar is the capital cost, and the red bar is the OM, operation and maintenance. So this is a technology that is basically all about fixed cost, right? It's very little variable cost. It's almost all fixed costs, and it is highly competitive, right? Of course, the complication comes from the fact that sometimes we don't have wind, and it may not have the ability to produce. So you can contrast that to go all the way down on this plot to a diesel fuel generator. This is the least efficient form of power production. You can see the cost is over $300. This is a plot that might be outdated by now. It's 2014, but more or less this is the same type of situation that we're facing right now. So it's always, diesel is kind of the last resort, because you're basically it's like burning perfume. It's very expensive. But it comes with a very relatively small capital cost. So it has very low fixed cost, whereas you have very high variable cost because the fuel is very expensive, right? So you're burning a fuel that is highly costly. In the middle, we have different technologies. So we have, for instance, a gas combined cycle. So after this bonanza of gas due to fracking, many countries were kind of not expanding their power systems with natural gas. But after this bonanza of gas that due to fracking, then gas became again a technology that is highly used for expansion. So gas, as you can see, has a blue bar that is about half the total annual levelized cost. And then, but gas is not cheap, so it's not as expensive as diesel, but it's also not cheap, not for free, like wind is. So it's a technology that is kind of in the middle of these two streams, right? So we have one stream, which is the onshore wind, very efficient in terms of levelized cost, with this intermittency associated with it. And the other end, we have the diesel fire generator, which is very expensive to run, but very low capital cost. And if you have the fuel in store, you can rely on it any time. And then in the middle, you have the natural gas plants that are, well, they rely on pipelines, a system of pipelines that are going to bring the gas from the wellheads to the actual site. And they don't have as high a capital cost as the others, but they also have this or middle range fuel cost. Okay, so how is this market? How does the market clears every day? So on a daily basis, all these technologies are competing to be dispatched, right? So power generators are trying to bid in Texas, for instance. They submit their bids with a day anticipation to the ERCOT. And what ERCOT does is it produces a forecast of demand. So this is you can see this is the demand during the day. So in the early morning hours, demand is relatively low. This plot is actually I think it's from PJM. So these values are not quite the values of Texas. Texas is lower than that. And then as the day progresses, then demand goes up all the way to the peak. So typically you would have a peak, in this case, about the 5 p.m. And so the economic dispatch essentially works in that we use the cheapest resources at the bottom. And these are the ones that have very low marginal cost, renewables. And so as we saw, renewables have, if there is wind, there's basically no marginal cost. All you're trying is to recover your capital, right? All the way to the stream, which is the most expensive resources in terms of variable cost, which are in this case, the gas-fired turbines. You can see that there is no diesel because in a regular day, no electricity market would ever rely on a $300 plus resource per unit of production. So on a regular day, this peak demand could go further down. This is what I wanted to use my iPad to show you a few variations on this plot. And so imagine that there is it's a spring day where temperatures are mild and there's not that much demand for either heating or air conditioning. And so the peak demand may not be, as it is portrayed here, as 130, but rather say 110. If it is 110, then the technology that would be at the peak, the marginal technology, would be the combined cycle. And in that case, that marginal cost of the system to meet demand is 35 as opposed to 120, right? So on a hot summer day, we have to use all of the resources, and because demand is high, and then that's why you see the marginal resource has a very high cost, whereas on a regular, mid spring or fall day, that's not the case, and then we use as a marginal resource something like a combined cycle or other resource of a similar nature that has this lower marginal cost. Okay, so far so good. Any questions regarding the way electricity markets operate?
Yeah, I have a question about,
yes.
You showed batteries on the slide before that, storage.
Mm-hmm. Yeah.
Is that just for solar, or is that?
Well, there are there are cases in which they are used as an independent resource, right? So this is just it's outdated. You can see it's 2014. This cost may have gone down, but still they're not quite as economic, and they also have limited capacity, right? So you can see why would it be useful to have, if you are dispatching a set of resources, you could conceivably charge the batteries in the cheap hours in the morning, right? And then use that energy in the peak to try to offset the higher cost of the resources that you otherwise would have needed during peak hour. So as market maker, if you have resources that have this ability to charge during the cheap hours and then deliver the energy, give it back to the system in the high price hours, this is very useful. And in fact, there are markets that have these pumped storage plants, hydro plants that essentially do that. They pump water in the early morning hours, and then they release the water back to generate electricity to move the turbines when the electricity is expensive. So in a sense, pump storage is a technology for storing electricity. Not quite like batteries, but in the end, it's the same type of operation. Okay, so let's move on. So what I wanted to do this is to show you now how is it that a market would deal with the issue of how much to invest. What is the market? What are the market levels of investment in different technologies? Right? What should we expect from the market in terms of investment in different technologies? Well, as you can imagine, if you have, if this is the forecast for a regular day in the market that you're considering, you can see that the marginal technology, which essentially is going to be setting the price, is never going to be much more expensive than $120, right? So if that is your expectation as an investor, then there are many of these technologies that are already out of consideration, right? Like for instance, diesel generator. Why would you invest in a diesel power plant if your expectation is that prices are never going to be above $120, and they're only if they are going to be around that range, it's only going to be for a few hours during the night or the late afternoon hours, right? So you can see that an investor looking at a market is already going to start discarding some of these technologies, right? Because some of them don't make sense given this type of expectation or forecast on prices. And so what I wanted to do is to tell you a little bit about a plot that used to be the way this is the way I was taught when I was taking my economics of power systems course in the 80s, as to how you should plan capacity or optimal planning of capacity for a power system. And so you would compare all the technologies, right? So you have technologies that are called base technologies that have a relatively flat total cost, right? Because they're mostly all about capital. And so if in the x-axis you have the total time during the year that you're going to have them running, you see that the slope of the base technologies is relatively flat because these are mostly capital. Their fuel, in the case of wind, for instance, the wind is whatever you can get on average for a year. That's what you can produce. But in the case of nuclear, the fuel costs are relatively small, right? So these are technologies that are called base technologies. Then you have the mid-merit technologies. These are technologies that are not as high on fixed cost, but much higher or relatively higher variable cost. So that's why they have a bigger slope, right? And then you continue to go to peak technologies. Now, peak technologies are ones that have very low fixed cost, but very high variable cost, right? And then finally, you have the backstop technology, which is outage, right? You might be forced to take the hit, take the cost of not being able to supply consumers for a certain amount of time because it's the economic thing to do. In particular, if you look at this first range, H naught, right? That's a range of hours. That if you compare the values of these total costs, the cheapest technology, if you are expecting to run a plant only for these few hours, let's say, between 1 and 20 hours a year. So this plot tells us that what is the most economic technology is to curtail demand, right? Incurring the costs of having to do an outage. Because, you know, if you estimate the cost of an outage, let's say in the state of Texas, this is estimated to be $9,000 per megawatt. That's still less than what it would cost to produce only for 10 hours using all the other technologies, right? So if you go from the left to the right, if you go to the second interval, the one interval that between H0 and H1, then this is an interval of hours that is between, let's say, 20 to 200 or 300 hours a year. Still a small amount of hours, but now it no longer makes sense to curtail demand. It makes sense to use something like a diesel fired power plant, which has very high variable cost, but it's going to be used only for this relatively limited amount of time. And as you can see, then if you move to the third interval, right? The third interval now, we're talking about significant fraction of the time in the year. And in that case, the optimal technology in terms of total cost is the mid-merit technology, which could be, for instance, the gas with combined cycle. And then finally, the last interval is those technologies that are going to be really operating almost all continuously, and those are the base technologies, right? So with this in mind, then we look into a forecast for demand. And this is a kind of a representation of demand that is not quite like what we saw here. So this is the time representation of demand. This is demand over time, right? So what we're going to do now, so imagine that this is the same day happens all throughout the year. It's the same type of demand. So this is a representation that is a little bit different, but it says the following. It says, if you look at H naught, then the value in red is how often within that day we would have a power demand that exceeds that value on the y-axis, right? So you see it's a big value, but it's only for a few hours, H naught. So for instance, let's go back here. H naught in this case will be, let's say, between hour 14 and hour 18 or 17, right? That's H naught. So only 4 hours a day. At 4 hours a day, you'll have a demand that exceeds 130 megawatts or thousands of megawatts. This is PJM values, right? So this first value here corresponds to that peak. And then as we keep going, right, if you consider another window here, let's say from the hour 8 or say noon to midnight, then you see the value is 110. So here it will be H1, 110, and so on and so forth. So if we plot these points of intersection between the technologies, the total cost of the technologies, and map them back down to this representation of demand, this is called in the industry the load duration curve, because it tells you what should you expect in terms of duration for what levels of demand. But what this plot does, then connecting these two plots, it tells us what we should do in terms of economic efficiency, in terms of technologies to supply demand at the minimum cost, right? If we put all these things together, this is what it looks like, right? So it tells us that the optimal expansion or the equilibrium capacity expansion in a market that is perfectly competitive, where there is no market power, no one player is abusing or determining the terms of trade, but rather everybody's competing. The level of investment in each one of these technologies that we should expect is what we have here, right? So we should expect a certain. So the first interval, the first value in the curve in the middle is how much of base technology we should expect. Then it says you should add to that chunk of base technology the next chunk of mid-merit technology, and then peak technology. But what I wanted to show you, the whole purpose of this exercise is to show you that in an optimal planning, capacity planning exercise, there is always going to be the possibility of curtailment, right? Even when you plan optimally, right? You always are going to have certain expectation of a few hours within the year where you will have outages. And why is that? Because, well, it is technically impossible to guarantee, well, it's economically inefficient, but it's also sometimes impossible to guarantee that you'll have all the resources to your to your disposal for this purpose, right? So the point that I want to make is that any market, any electricity market, has this risk embedded into it, right? Any red event, which corresponds to a day in which this curve all of a sudden has a much higher peak, a peak that doesn't go to 130, but let's say to 150. That's a rare day, right? It's a rare occurrence, but that rare occurrence is going to be met by the appropriate technology, which is, well, we have to curtail, we have to turn the lights off because it's an event that the system was not able to withstand, and it's a very rare event. It's a low probability event. In fact, in the old days when the industry was regulated, this reliability standard was set for by the regulators, by the government, and the government would say, and in the US, is 1 day in 10 years. That's the amount of outage that is acceptable from the point of view of the government. Okay, so having said all this, then we have a picture of what to expect from the market in terms of investment in different technologies. And this includes the possibility of a very short-lived rationing, right? Curtailment. And the curve at the bottom shows you what is called the price duration curve. So which is the technology that is at the margin at every hour, depending upon the duration. So just as we saw here that in the early morning hours, renewables or nuclear were the marginal technology, because when it's 4 a.m., you're basically relying on wind power and maybe a little bit of nuclear. But when it is 5 p.m., you're using everything, and then the cost goes all the way up to 120. Likewise, then here this shows you what to expect, what an investor would expect when considering investment in a new technology. So an investor investing in the state of Texas, for instance, would see that for a significant amount of time, the state of Texas is highly competitive market, meaning that the prices are going to be very low. And then for a very small amount of time, and with high uncertainty about how long is this amount of time, that investor could expect very high prices, namely the value of load, the VOLL, the value that is set by the ERCOT as the estimate of what it costs to the Texan economy to not be able to provide 1 megawatt of power. And that is, right now, is $9,000 per megawatt. So up to this point, what I have shown you guys is what we should expect in terms of reliability from a market. Right? So now I'm going to then go into the details of what happened in Texas and why did we have what we had. So in the old days, when this was all, when investment decisions were the result of a negotiation between utilities and the regulator, this is the terms that people would use back then. It would be security of supply or resource adequacy, meaning you have to invest in a way so that you meet certain reliability standards. As I said, in the US, this standard was set to be, in the old days, 1 day of outage for every 10 years of operation. And so sometimes people use security of supply because it's used mostly for short-term operation. So in the very short run, like next day or next week, how likely is it that we're gonna have insufficient capacity? If that is the case, then we are talking about our supply is not secure, right? If we talk about long-term, then people prefer to use the term resource adequacy because long-term is all about investment. And if we have a forecast for growth in demand for the next, say, 5 years, and we have a picture of the investment, the expected levels of investment by all utilities participating in the market, then you could make an assessment as to how adequate is the market activity in terms of investment to meet the expected growth in demand. Okay, so And here's the problem. So the problem that happened in all electricity markets is essentially the following: that because electricity is such a basic necessity, most electricity markets will impose a price cap on the spot price for electricity. Right. So to avoid any market power abuse, what regulators will do is say, okay, let's create this market, let's let it run, let's let it determine what is the cost of electricity at each hour within the day as a result of these market forces, but we're going to cap it. We're going to cap it because we cannot allow it to be to exceed a certain amount. Right? But what this did then is essentially it diminished the incentives to invest. Remember, this is the picture that I showed you earlier with the expectation of what prices, how long periods of time should I expect different prices. If you impose a price cap in red, then you're basically taking that chunk, that rectangle on top is a amount of revenues that are missing, right? You're basically taking revenues that could have been made by participants, generators, that are now never going to materialize. And this affects everybody, every technology, but it most definitely affects peaking technologies. If you were considering on investing in a technology that was only going to be used for a few hours within the year, namely within the intervals H0 and H1, and then the government came and imposed this price cap in red, that's basically a killer proposition, right? You're saying, well, now it doesn't make sense for me to invest. It was already difficult to rely on funding an investment for a plant that is only going to be operated for a few hours within the year, based upon that expectation of high prices. If you come in and limit those prices, then this is no longer an economic project. And so ERCOT's approach was, we cannot do that. We cannot put a price cap. Unlike what people have done in other markets, ERCOT decided not to put a price cap and to basically let the price cap be the value of lost load, essentially be the ceiling in terms of what a generator can earn is essentially the cost of electricity non-supplied to the economy, the value of lost load. So that's ERCOT's approach. It's also referred to as energy-only approach because, as you can see, what they're saying is we don't need anything else to promote the right levels of investment, because by allowing spot prices to reflect the scarcity, right, then investors that are looking into providing these technologies, these peak technologies to the market are going to see, well, yes, it makes sense to put this plant in small scale. It's only going to run for a few hours a year, but I'm going to be allowed to charge high prices because that's when I'm going to be able to recoup my investment. There's a second side to this, which is that retailers, remember, retailers are the intermediators. Retailers are intermediating between bulk power generation. They buy power from the bulk generation, and then they sell it retail. And so this intermediation is a risky business if prices can go up, right? So you rather have very limited risk in terms of prices and sign a forward contract with a generator that says, you promise to deliver this much power, and then at this price, and then if the actual spot prices go above that price, it's your problem, not mine. So as a retailer, I'm covered. Of course, I'm going to pay a certain premium on that price because it's a form of insurance. So what ERCOT did is, okay, let's make sure that the scarcity is going to be reflected on the spot price, right? And this is a mechanism called operating reserves demand curve. It's a form of intervention. It's a form of regulation because, as you will see, what it does is the following. It says, when the operating reserves in the state of Texas, in the market, ERCOT, is below $2,000, then the spot price, regardless of the way people are bidding, is going to be set at the value of lost load, which is $9,000 per megawatt hour. This picture shows this is the operating reserves demand curve. So on the x-axis, you have the level of reserves, So when the storm hit, these reserves were below 2,000 megawatts, which meant, well, they were the hours before the storm, they were already down significantly, but after the storm basically took out all that capacity, then this rule by ERCOT ensures that the price in the market is going to be equal to the value of lost load, which is $9,000 per megawatt. Keep in mind that on a regular day, on an average day, electricity in Texas is traded at values between $30 and $40, $50 per megawatt. This is $9,000 per megawatt. Okay, why do we do this? Because, well, this incentivizes people to invest in technologies that are going to be able to produce at that moment, or to enter into long-term contracts that would protect them from that price risk. Now, but it's interesting to see that this doesn't stop there, because the state of Texas also have this other intervention, which is that for values of reserve that are not as high, not as low as 2,000 megawatt, but not as high as to allow them to be, not worried about things. What they did is that for values between 2,000 and then 6,000, they're gonna make sure that the price in the market is equal to that value in the blue curve. So it's in a sense a form of intervention. So we are told all the time that this is one of the most competitive markets, and it is a competitive market in Texas, but there is a lot of regulatory intervention here. This regulatory intervention goes in the sense of making sure that the prices are going to be high enough, because the idea is that this threat of high prices is what is going to incentivize investment. Okay, the problem that ERCOT suffered is that there was missing insurance. As I said, retailers can cover the risk of exposure to high prices with long-term contracts, right? And these long-term contracts work in the way that these are financial contracts, in the sense that, for instance, I strike a contract with A, strikes a contract with B, and according to that contract, A is going to deliver to the market a unit of 1 megawatt at $45 per megawatt. Well, if the spot price is less than 45, then of course doesn't make sense to have the A produce at 45, right? Or at whatever cost was. A could conceivably simply buy from the spot market and sell it and give it to the retailer, right? Whereas if the spot price is above 45, then this generator is going to have to produce at their cost. A is going to receive 45, but it's essentially either going to be exposed to the higher price or produce at their own potentially lower cost. So all the price risk under a long-term contract is assumed by the generator, and the retailer is covered against the price risk. So this is the example here. So if a generator is contractually committed to sell 1 megawatt at 45, and it turns out that the spot price is much higher than 45, for instance, 9,000, well, if the generator is not able to produce, because that could happen, then that generator is going to be liable for the $9,000. So if you have a contract like this, and polar vortex is in the makings, and I'm a generator, I better make sure that I have a properly winterized plant, right? Because I don't have a properly winterized plant, and I am short, in the sense I have committed to sell this amount at 45, I'm going to lose a lot of money. I'm going to have to assume the $9,000 cost and receive in return only $45. So this is the idea that was supposed to support investment to cover a rare event like the polar vortex. But this didn't happen, because retailers in Texas have no obligation whatsoever to cover their price risk. And so let me show you that this is a headline from Bloomberg. After the storm hit, so you can see here, this is February 15. right? So the day after the storm hit, retailers such as this retailer here, Greedy, I mean, it's Greedy, not with double E, but Greedy with I. They were essentially retailers that were simply buying from the spot market, which is very risky because the spot market can go as high as $9,000, and then charging those prices to the consumers without any long-term contract, without any price insurance or hedge. So when the storm hit, what they did is they went to the customers and told the customers, you better find out another provider because we're not going to honor our contract. I mean, we're going to bail out of the contract to supply you with electricity. Of course, how can they continue to supply electricity on $9,000? This is essentially crazy. So the problem with that is that the system was exposed to a systemic risk. Right? There were many retailers out there that had not purchased any form of price insurance. As a result, because there was no demand for price insurance, many generators were not incentivized to winterize their plants because they were not exposed to those risks. They knew there was this rare events that could alter their capacity, but if you have not sold forward your capacity, you don't have any risk. You have the risk of course of not being able to produce, but only for a few days because these polar vortex events have never happened for a duration longer than a few hours, as it was the case in 10, 15 years ago. So in a sense, the whole problem was a systemic risk that was the result of not having retailers be protected in terms of price exposure to this rare event, which percolated through the system to the point where generators on the other end had no incentives whatsoever to winterize their capacity. And we were exposed to that systemic risk. And when the event took place, then this is what happened. So this is very similar actually to a banking systemic risk. As you know, in our financial system, banks are repeatedly subject to testings. This is called in regulation of banks. Is essentially the regulator looks at the portfolio of debts and loans outstanding and the amount of capital that the bank has, and then they simulate a situation where the economy tanks and people are not paying. And so this simulation is supposed to identify what is the level of risk that bank is essentially taking on. Because if all the banks in the economy are taking high risks in their portfolios, then chances are that if the economy is affected through a shock, like a pandemic, for instance, then all these banks are going to go under, and the system as a whole, because banks are lending in turn to themselves and borrowing from themselves, then they're going to basically collapse. So this is why we have that type of regulation in the banking system. So what happened in the state of Texas is that we didn't have a similar type of regulation to prevent this systemic risk from materializing. Okay, so what is the solution? As I said, I think I'm running out of time. I won't be able to finish, but at least I'm going to cover the capacity market part. In many countries around the world, this similar phenomena as to what we just went through in Texas has occurred. So it's not like we are alone in this. They have then came up with solutions, and these solutions can be classified into it's called capacity markets, and they can classified into quantity-based versus price-based. So price-based are kind of heavy on regulation because it's essentially the regulator paying a price to generators to make sure that they are going to have the capacity under certain stressful conditions, right? So it's heavily relies on the government regulating. Whereas on the left-hand side, we have approaches that are more akin to markets. And let me zero in on the one on the bottom, which is the one that is currently in place in Pennsylvania, University, Maryland, and in New England. New England ISO also has this scheme. What is it that they do? This is what they do. They define capacity. And capacity is a particular form of financial obligation, which is that you're gonna have to produce, you're gonna be paid a certain amount. This is separate from the electricity energy sales, right? If you're a generator, you can receive revenue from selling power, but in these markets, you're gonna also receive revenue from selling this capacity product. And what is the capacity product? Is something called a reliability option. Reliability option, what it does is the following. It says, under certain conditions, critical conditions, you are obligated to provide this amount of capacity to the market, right? In return, regardless of what you actually produce, you're going to be paid all throughout this time before the event happens a certain amount. So it's kind of like an insurance scheme. It's an insurance against a certain critical event, and the system as a whole is paying for insurance. And if the event takes place, actually, then the insurance kicks in. The generators have to supply the capacity to the market, and this is how the system is going to be able to withstand the emergency situation. Of course, the cost is going to be passed through consumers, and this is why perhaps it wasn't as desirable for the initial design in Texas, because it means that we need an additional type of payment to generators to guarantee a certain level of reliability in the market. Now, these designs are not without its technical complexities and criticisms. For example, these reliability capacity options are procured through a competitive tendering scheme. So every so often, market maker, in this case PJM, would query the generators to bid into these auctions for allocating these capacity contracts. And so there is some sort of a demand that they use, which is not quite a demand, because nobody is being asked, no consumer in the area of service of PJM is ever asked as to how much are they willing to pay for reliability. They decide this curve, which is kind of a demand. That's why I put demand, quote unquote, for reliability. So you see in the x-axis is the good old 1 in 10 standard for reliability. So they're keeping the standard that was from the old days of regulated industry. And they say on the y-axis, this is the price we're willing to pay. This is the price the market is willing to pay for a standard associated with 1 day in 10 years. On the left-hand axis, that point is estimated. It's called the cost of new entry, CONE, cost of new entry. So they do an estimate of what would it cost under current conditions to invest in an efficient plant for generation plant, and that is the value that is set for this point in the curve. The remaining parts of the curve are totally ad hoc, but this is what they use for this auction, which starts out at a very high price, and then generators are bidding up until it crosses this threshold of this curve. And then that's when they say, well, we have enough capacity obligations in the market to guarantee that we have our reliability target met. Okay, so I think I'm running out of time, and I wanted to give time for a few. I wanted to mention also market coupling, and let me say just a few things about this. So market coupling is essentially the following. This is the picture of the state of Texas during the outage, the number of outages right after the event, the polar vortex event. So as you can see, there are New Mexico and Oklahoma were basically doing fine. They didn't have as much problem as the state of Texas. Louisiana did have some, as well as probably Arkansas, but not as much as the others. So this suggests that if the state of Texas had some interties, some interconnection lines with these markets, then they could have helped us. They could have, this market would have been able to export power to the state of Texas and so diminish or mitigate the outages. But the state of Texas did not have those interconnection lines. And so the next question is how to structure these economic and technical exchanges of power with adjacent markets. And this is in Europe, they use the term market coupling, because as you can imagine, Europe, so many tiny countries, there is a lot of power exchange between countries. So France, Netherlands, and Belgium, they have a very tight coupling. So they have separate markets, but they exchange power all the time. This also allows them to handle the intermittency of wind power. You know, Denmark has a lot of wind power. So Denmark exports to the Netherlands, and then when this is very cheap power, but when Denmark is out of wind power, then the Netherlands have to then buy from Belgium or France, and so on and so forth. Anyways, I wanted to say a few things about that, but let me go ahead and conclude. So the energy-only approach to security of supply and resource adequacy in ERCOT has to be revised. This is something that I think everybody agrees. Before the polar vortex event, there are still voices in the arena that would say that ERCOT was fine, that they did not need any other form of regulatory intervention, such as a capacity market. But I think one way or the other, something like a capacity market is going to have to be implemented to be able to address the concerns of security of supply and resource adequacy in the state of Texas. And also, the state of Texas has to look into the possibility of being able to schedule power flow, power exchanges with through interconnection lines with adjacent markets, because this helps mitigate exposure to risk. And so this is a tricky political issue, because once you have interstate trade, this power exchanges between markets is a form of interstate trade, then you are going to be subject to federal regulation. And I believe that's one of the reasons why there was no significant interconnection with other markets. But this is clearly a way to improve the reliability of the market in the state of Texas. So with that, I want to stop and maybe entertain a few questions.
With the announcement of the solar farms that they're planning in Iola, will that help the capacity to any degree?
Well, new capacity is always good for any, it's always good to have new capacity coming in. But the problem is solar is likely not to be of any help if the challenge, if the situation arises, say, at night, right? So it does help to mitigate, but it may not be the right tool to rely upon to address this kind of emergencies. So that also is tied to the question of what do we mean by capacity, right? So in the old days, capacity was a concept that was fairly tied to the technology, to the power plant itself, right? So if I invest in a plant and the plant has a nominal 100 megawatts, and I have to take it offline for a few days during the year, then let's say I have a capacity factor, so I would be able to use this plant for 85% of the year. Then I would say, of the 100 megawatts, my capacity is 85. Right? Well, it turns out that that's not appropriate concept to look at capacity, because capacity is a system property, right? It's the ability to deal with the disturbances as a system, as a whole. So you have to come up with a different measure of capacity that could capture your contribution to the reliability of the system as a whole, right? So this is a challenge, because if you were to measure, or if you were to use this old notion of capacity for, say, a wind farm, right? you could end up saying of a wind farm that has 100 megawatts of capacity, I can only rely with probability 1 with very limited amount, like it would be like 5 to 10, 15, 20 megawatts at most, right? Because, the wind power is highly volatile, even though, there are times in which it produces full capacity, there are times in which it produces nothing. And so this could be construed as to saying a wind power farm doesn't really give me a lot of capacity in terms of reliability, but that could be misleading, because all that matters is at the end of the day, what matters is how does it contribute to the overall reliability of the system. It could be that wind is significant when other technologies are not as important, and then you could have like the contribution to capacity by wind is significant. So it's an open question. I think the question of what is the capacity of renewable plants? I don't think that we have a consensus on that.
This sounds like kind of a simple-minded question, but if I were an investor and I wanted to make some money, wouldn't you want to buy power when it's available during the off hours and store it and then sell it at incredibly high prices?
Well,
yeah, definitely.
The storage is therein lies the problem. And I know there is quite a bit of research, if you want to call it research, into storage schemes, or systems. You mentioned pumping water, but also air. Some places they have pumped air into salt caverns or just into big tanks. And even such a simple thing, and this seems to me, I'd really like to know more about it. I've heard only a little bit about it. A strictly mechanical sort of a system where you, with cables and electric motors, pull up huge weights, when the price of electricity is low. And then when you need it, the weights come back down and the motors become generators to generate electricity. So it's basically the same thing as pumping water, but just a strictly mechanical thing, like an elevator. The elevator takes power when it's going up and it gives power when it's coming down. That seems to intriguing to me.
Yeah, there's flywheel systems.
Flywheels, another.
And these things all sound like they're fairly elaborate, but if you know what goes into making a nuclear power plant, this is very low tech stuff and incredibly low cost. I think these compressed air systems, everything is off the shelf. It's all stuff that's used for refining oil and other chemical plants. There's nothing you have to buy that has to be made specifically for that.
Yes, there's a lot of the term demand response is essentially a generic term for all technologies that essentially help you to respond to high levels of prices. And storage is one of them, but there are other technologies, for instance, that would control the household appliances and the cycles upon which you run the appliances in a household in response to forecasts for electricity prices. And that's another way of introducing an element of flattening the demand for electricity, so that you don't have these peaks that are essentially causing so much trouble.
It seems like it would be simple to get rid of all these problems with reliability that are associated with this peak hour cost.
Yeah.
Just get rid of that peak hour cost one way or another.
Yeah.
And then you have.
But the problem is we still don't have storage capacity in large scale, in economic fashion. That's the problem, right?
But I think I'm just wondering where the economy is. If it sounds like there's there is a big price increase from going from low cost power to high cost power.
Yeah.
I mean, where is the economic breakpoint there? I know. So I know that does Texas have any pumped hydro?
I don't know. I think not.
Yeah. I know you know, so in California, basically they do as much as they can. They're limited by the fact that they're under like a 40-year drought. So
Right.
all of their reservoirs are below capacity.
Yeah, and pump storage is also environmentally tricky, right? You may
yeah, it is,
have
and it's limited too. There's really, it's pretty much been built out. There's not going to be a lot of new pump storage being built, but they have these enormous power surpluses during the day.
Right.
Everybody's got solar panels. You know, a lot of people have solar panels, and during the day they're giving away electricity. You know, paying people to take electricity.
Mm-hmm.
Well, there was also talk, you know, and this goes back several years ago, that as the number of electric vehicles increase, that you would recharge your electric vehicle when electricity was cheap, but then the battery in the electric vehicle would feed back into the grid, you know, when electricity was expensive. But I haven't heard anything about that in a long time.
Eventually, that will be when the fleet is mostly electric. We'll see that. Right now, I don't think that's the case. But
no,
the state of Texas is facing a problem right now. Something has to be done. And so, if you see the legislative initiatives, a lot of them are essentially related to capacity markets and or even also allowing, as I mentioned, interconnection with neighboring markets.
Yeah.
So I think this is where the regulation is likely going to go in the next few years, and it's not without its own technical challenges. So we have to be prepared to.
I think my question would be is how much is the regulation development being driven by engineering versus just by the way things have been done? And
you're totally right. It's almost 100%. So I know that because I'm an engineer. So when I worked for the regulator, I had to sit with lawyers and economists, and we would never agree on anything. And that was an eye-opening experience for me. So what my view is that yes, engineers are good at give me your problem and I'll give you a solution, right? Cost, not so much. I mean, of course, you want to try to minimize cost, but then the notion of we have a supply chain that is being pushed top down, right? So bulk power generation and then transmitted down. Whereas what we are seeing is more and more the ability to generate in a distributed fashion, small scale. So this is a challenge for engineers, power engineers, because they have been educated to think in this way, right? You know, power goes from large power plants and is transmitted down to small consumption. Whereas now it's a flux between some power is produced distributed locally and some power is produced large scale. And in between, you have to make sure that this operates seamlessly, and that's not easy. So I think this is the research challenges that power engineers are facing nowadays. How to adapt to this world in which the world is moving beneath you.
Yeah,
right? It's no longer as you have this anchor on a huge power plant that would serve as the basis for everything you do. You can always rely on having that slack bus. They call it the slack bus in the jargon, because everything that you cannot cope with, that's going to be assumed by the slack bus, right? And there's no longer going to be a slack bus because there's going to be a whole federation of producers that are going to be relatively small. That's hard. That's going to be a challenge.
Well, this was very interesting.
Okay.
Thank you very much.
All right.
Certainly an interesting presentation.
Okay. Thank you. Very much. Thank you so much. All right. Okay. Bye. See you.
Yeah.
Bye.
Thank you.
Bye.
Very interesting. Yeah.
Bye.
Thank you.
Go out and help someone is the best we can do. There's someone who needs someone